Next up, we are going to tackle atmospheric stability. Before we get going though, let's recap some information about the troposphere from previous lectures. The troposphere, as you know at this point, is the lowest of Earth's atmospheric layers. It's the layer in which we live. It's where all the weather occurs, basically, and it is an area of strong vertical mixing. That's because the sun is warming the Earth's surface, which is in turn warming the overlying air, and that air, as it warms, begins to rise. And we get that vertical mixing up and down. Most importantly, in the troposphere, the temperature decreases with altitude. Very important. Equally important to atmospheric stability is the fact that air pressure also decreases with height, and both of these things combined contribute to the stability of the atmosphere. Let's see how. Honing in on the factors that influence atmospheric stability. On this slide, we've got two steps. The first one has to do with air density. So an air parcel that is warmer has lower density, and an air parcel that is colder has higher density. And an air parcel, here we're talking about a body of air that has specific temperature and humidity characteristics. So how this works is when air heats up, the air molecules start to move faster and they spread out. And the increased movement causes the air to expand, and that lowers its density. We have more space for those air molecules to move around. Cold air has slower moving molecules that are more tightly packed. It can squeeze together, making it much denser and basically heavier than warm air. So this is why warm air rises. The other thing we've got going on are two opposing forces that are always trying to balance each other out in the atmosphere. The first one is the upward buoyant force. Buoyancy is that force that allows objects to float in a fluid, and in this case that fluid is air. This is why boats float on water. This happens because the fluid, air here, is exerting an upward force and is kind of counteracting the air's weight. Meanwhile, we all know what gravity does. Gravity wants to draw things down towards the center of the Earth. So gravity is pulling down while buoyancy is pushing up, basically. So we've got differences in density and these two opposing forces working on this air parcel. Let's take a look at the next slide that gives you kind of a better look at it. So we've got three different things going on here, and bear in mind in the atmosphere, these three things are all happening simultaneously. We have the effect of those two opposing forces, buoyancy and gravitation. We have the influence of density on an air parcel, and we have the influence of air pressure. These little blobs here represent our air parcels. So if we start on the left, our little air parcel is hanging out in the atmosphere. If nothing is mechanically moving it, and it is the same density as the air around it, as long as the buoyancy force and the gravitational force are equally balanced, that air parcel is not going to move. But if gravity becomes stronger, it will be moving downwards toward the surface. And if buoyancy becomes stronger, it will be moving upwards towards the heavens. What forces could work on that? Well, one of them is density. So let's look in the center here. We've got our two little air parcels. If you look, parcel A on your left, the higher density one, look how tightly packed those little air molecules are. This parcel is essentially going to be the heavier of the two, and it's going to be colder generally, and it's going to be more likely to want to sink down. On the other hand, our second one, parcel B here, the lower density one, is probably much warmer. And notice how spread out the molecules are compared to the other air parcel. It is lower density. Therefore, it essentially weighs less than the colder air parcel. Because it weighs less, it's going to be much more influenced by buoyancy. It's going to want to go up. As long as it's lower density than the air around it, it's going to want to continue going up. Meanwhile, and at the same time, we have the air pressure aspect. So your higher air pressure is going to be closer to the surface because you have all of that air all above you up to the top of the atmosphere pushing down on you. As you move away from the surface, that air pressure is going to become lower and lower because there's less air above you. So it makes sense. Now next, we're going to focus on expansion and contraction of air parcels. And this is going to bring into play something called adiabatic processes. This is going to be a new and important concept for you. Remember that air gets colder with height. So, as your air parcel rises, it too will begin to get colder with height. So what we're looking at right here is kind of that warmer air density idea. This very cool picture here is of a hot air balloon festival in New Mexico. If you know how a hot air balloon works, they get the balloon, it has some air in it, they turn a burner on and it heats up the air inside the balloon. It makes that air inside the balloon much less dense than the air around it, and it begins to rise. This lets the balloons become buoyant and do their thing and float away. But bear in mind that the balloon is trapped and it has a constant source of heat keeping it afloat. But with air parcels, they don't have that constant source of heat because as they're moving away from the Earth's surface, they're losing the warming of the Earth's surface. So as they rise, they begin to expand because air pressure is decreasing as they go up higher, and as they expand, they begin to cool. And this slide is just repeating what I said in the last one because it's super important. As air parcels rise, they expand, and as they expand, they cool. The opposite is also true. If an air parcel is pushed down, it's going to contract and it's going to start warming. Now, the interesting thing about adiabatic processes is that they lead to temperature changes within an air parcel, but not through any exchange of heat energy. There's no heat energy being exchanged between the air parcel and its outside surrounding air. With adiabatic temperature changes, it is all about air pressure. And this picture we're looking at here gives us a good example of that you may have experienced yourself. This young lady and her family live in California's Central Valley. They very much enjoy camping in the Sierra Nevada mountains, just to the east of them. So one day they pack a picnic basket with a bag of potato chips included in the contents, and they head up from their home at sea level in the valley to their camping spot at 7,000 foot elevation in the Sierra Nevada. When they pull out the picnic basket, they discover that this bag of chips has puffed up to its max capacity. If it had expanded and gotten any bigger, it probably would have blown up. If they had opened it at that point, they would have noticed that its temperature was also slightly cooler than when they left. So what happened here? Well, as they went up from sea level to 7,000 feet in elevation, that air pressure around them in this bag of chips is decreasing a lot as you go up in elevation. Therefore, there's less air pressure being exerted on those chips and on the air inside the bag of chips. This allowed the air inside the bag of chips to expand.
Now, assuming they hadn't opened that bag of chips and they hopped back in the car and went home, by the time they got home and they pulled out those chips, they would have seen it was right back to its original kind of deflated state. Why? Because as they went back down the hill, the air pressure was increasing on them. And so it forced that bag to contract. It compressed it slightly. There would have also been just the tiniest bit of temperature, air temperature increase inside the bag once they got back down to the valley, as opposed to its temperature up in the mountains. Let's find out how this works.
So adiabatic basically means without heat. What goes on here is the temperature of an air parcel changes as it goes up and down in the atmosphere. But those temperature changes they're only occurring within the air parcel. They result from changes in the volume of the air parcel because of changes in the air pressure. But they don't involve any exchange of heat energy between the air parcel and the surrounding atmosphere. So we got two ways it can go here. We've got adiabatic cooling, which is the cooling of an air parcel through expansion, getting bigger, and adiabatic warming, which is the warming of the air through compression. So here's how that works. If we look at adiabatic cooling, that air parcel rises, the air pressures outside the parcel decrease. Those molecules inside the air parcel are exerting their own pressure outward, and because the outside air pressure is decreasing and the molecules are still exerting their own pressure, this causes the parcel to expand, and that process of expansion causes cooling of the parcel, and then the temperatures decrease. Now, if the air parcel starts to sink and starts to go down, we have the reverse thing going on. The air parcel goes down. As it goes down closer to the surface, that air pressure is increasing. That surrounding air pressure squeezes the air parcel and forces it into a smaller volume, and that compression causes the temperature inside the air parcel to increase. And the temperature changes within that air parcel that result from changes in its volume due to changes in air pressure are called adiabatic temperature changes. As those air parcels move vertically in the atmosphere, they cool or warm because of those changes in their volume. If you look at this image here, this figure from your book, this air parcel is cooling and warming at a regular rate. Its temperature is either increasing as it goes down, or it's decreasing as it goes up. As it goes up, it expands and cools. As it goes down, it compresses and warms. Let's take a minute and look at what's going on here. So just take a minute, look at this figure, kind of absorb what's going on here, and think about at what rate does the temperature of this air parcel change? How's its temperature changing with altitude? Just pause for a minute, check it out. What is its temperature at the surface, then at 1,000 feet, then at 2,000 feet? Well, it changes by 10 degrees Celsius per 1,000 meters. Check it out. If we start at the surface at 30 degrees Celsius and we go up 1,000 meters, our temperature is dropped by 10 degrees. It is now, that parcel is 20 degrees Celsius. If we go up another 1,000 meters, we drop another 10 degrees Celsius. So as you go up in from the surface towards the top of the atmosphere, you are subtracting 10 degrees Celsius for every 1,000 meters you go up. Works the same in reverse. If you want to push that air parcel down, you would then be gaining 10 degrees Celsius for every 1,000 meters. You start at 10 degrees Celsius at 2,000 feet, push it down 1,000 feet, you gain 10 degrees. You are now at 20 degrees Celsius. Push it down another 1,000 feet to the surface, you've gained 10 degrees Celsius again. So this regular change in temperature per every 1,000 meters is something we call a lapse rate. We are going to use 3 main lapse rates as we go through this section, and you're going to want to write them down and learn them because we're going to use them to do some calculations in a little bit that are going to help us understand and describe atmospheric stability. So we will take a look at each one. First off, we have the dry adiabatic lapse rate, the DAR. This is the one you just looked at. It's a change of 10 degrees Celsius per every 1,000 meters moved up or down in the atmosphere. We use the dry adiabatic lapse rate when we are dealing with an unsaturated air parcel, hence the name dry. So what we're looking at is the rate of temperature change within that parcel of unsaturated air. It still can hold more water vapor. It is not saturated. There is no condensation taking place because it's not saturated yet. Next, we have the moist adiabatic lapse rate. This is the rate we use when our air parcel is saturated. The moist adiabatic lapse rate is a lesser rate of change than the dry adiabatic lapse rate. This is where your temperature is going to change less with altitude when that parcel is fully saturated than it would when the parcel is unsaturated. So what do I mean by fully saturated? I mean your parcel is holding all the moisture it can possibly hold at that temperature. It is fully saturated. It has reached its dew point temperature. Its relative humidity is 100%. Its water vapor content is equal to its water vapor capacity. It can't hold no more. We use that moist adiabatic lapse rate once we hit this point. You will see different places maybe use, like different textbooks use a slightly different moist adiabatic lapse rate here and there, and it can change slightly from place to place. We're going to use a standard MAR, moist adiabatic lapse rate, of 6 degrees Celsius per 1,000 meters. And then finally, our last lapse rate is the environmental lapse rate. The environmental lapse rate does not pertain to the air within that air parcel. It describes the rate of temperature change with altitude outside the parcel. So the air surrounding the air parcel, the environmental air. You can hear it called the ambient air. Your environmental lapse rate, how much that outside air is changing, can change a lot from place to place, depending on the environmental conditions. Just basically, what are the conditions happening at that particular location and time. For our purposes in this course, we are going to stick to a set environmental lapse rate of 6.5 degrees Celsius change per 1,000 feet. Oops, I said per 1,000 feet. The environmental lapse rate is 6.5 degrees Celsius per 1,000 meters change. So that dry adiabatic rate, that 10 degrees Celsius per every 1,000 meters, and if you really want to know it in Fahrenheit and feet, there it is. But we're not going to use it because metric system is way easier for our calculations. The dry adiabatic rate is that rate of temperature change within the unsaturated parcel of air. The environmental lapse rate, again, is the decrease in the air temperature outside of the air parcel as altitude increases. The average environmental lapse rate is 6.5 degrees Celsius per 1,000 meters. Meanwhile, we need to revisit net condensation before we get too far into the moist adiabatic rate. Remember that net condensation is what occurs when your air parcel has reached its saturation point. Its water vapor content is equal to its water vapor capacity. Its relative humidity is 100%, and it has reached its dew point temperature. This is when we will have clouds form. So a good question at this point, if you ever watched clouds up in the sky, you notice they all stop, like the lowest ones, the ones closest to you, just stop dead at a certain level. So what level do clouds, what level do they start forming at? This is called the lifting condensation level, or the LCL for short, because it's way easier to say. This is the altitude at which that air parcel becomes saturated. So net condensation occurs when that air has been lifted, either of its own accord because it happens to be warmer than the surrounding air, or it's been pushed up by something. When it has been lifted and it is cooled to its dew point temperature. Above the LCL, that condensation that has occurred is releasing latent heat, the hidden heat, to the atmosphere. And that slows the rate of adiabatic cooling down to what we call the moist adiabatic rate. Our moist adiabatic rate is what we use when we are dealing with an air parcel that is saturated. It hasn't reached the lifting condensation level. It is completely saturated. Condensation is going to begin, so it is very full of moisture. As condensation begins, it is going to release some of that latent heat to the surrounding atmosphere, and that's going to warm that surrounding atmosphere a little more than it would be if condensation was not going on. That's going to slow the rate of cooling as we go up in the atmosphere a bit more than we see with like the dry adiabatic rate. So the moist adiabatic rate does vary given the situation, exactly where you're at. But for this class, we are going to stick with a moist adiabatic rate, an MAR, of 6 degrees Celsius per every 1,000 meter change in altitude. So that's what we're going to use. It might be a little different depending on, what's going on. For us, that's all we're going to use, but the moist adiabatic rate is always less than the dry adiabatic rate. And here's kind of what we're looking at with that, how those rates change. So we have an air mass is coming into this Tinakula Island, somewhere in the South Pacific. It's coming in off the ocean. The island itself is being warmed by the sun, and that combination of things, the air being kind of forced up over the mountain there and the warming air right over the surface, that air is going to start rising. And as it rises up, if we were calculating this, we would use the dry adiabatic lapse rate because it's not saturated yet. Once it gets to the lifting condensation level, boom, it has all the water vapor it can hold. It's going to start condensing. And from that point forward, as we go up in the atmosphere, we are going to use the moist adiabatic lapse rate. All right, and now we are going to use this figure from your textbook to figure out some lapse rates. How is the air parcel temperature changing as it moves up or down in the atmosphere? So let's kind of orient ourselves. We have an air parcel. It is moving up into the atmosphere from the land surface. From the surface to the lifting condensation, that parcel is not fully saturated. It is unsaturated. It still can handle more water vapor. But as it rises, it's going to cool, it's going to expand, it's going to be able to hold less water vapor. And once it reaches the lifting condensation level temperature, the lifting condensation level rather, hits its dew point temperature, we will have condensation beginning. At that point, our parcel is fully saturated. We are going to have to switch to the moist adiabatic lapse rate of 6 degrees Celsius per 1,000 meter. Let's figure out some lapse rates. Before we do that, we have to know one very important thing, which is what is the dew point temperature at which this parcel is going to become saturated and start condensing. So for this example, let's say our dew point is 10 degrees Celsius. That's the point at which our parcel will become fully saturated and start having condensation going on. So next, let's say that our surface temperature, our parcel is going to start out at 30 degrees Celsius. So here we are at the surface, 30 degrees Celsius. Our air parcel is unsaturated. It still has room to hold more water vapor, but as it begins moving upward, it is going to cool, and its capacity for holding water vapor is going to go down. So we are unsaturated, dry adiabatic rate. We're going to go up to 1,000 meters. Our temperature is going to drop by 10 degrees Celsius, that dry adiabatic rate. So at 1,000 meters, that is going to give us 20 degrees Celsius. We're still unsaturated, so we're still using the dry adiabatic rate. Go up another 1,000 meters to 2,000, which brings us to 10 degrees Celsius. But we are now at our dew point temperature. If you look over to your right, that's our dew point temperature. So we just hit our lifting condensation level. Our parcel is now fully saturated. It can't hold any more water vapor, and it's going to start condensing the water vapor in there to liquid droplets. So from this point, from the lifting condensation level upwards towards the heavens, we are going to use the moist adiabatic rate, at least until we hit the stratosphere. So we are now going to subtract 6 degrees Celsius for every 1,000 meters we go up. So we're starting now at the lifting condensation level at 10 degrees Celsius. We go up another 1,000 feet. It's now gone down to 4 degrees Celsius. Go up to another 1,000 feet. And remember, we're taking away 6 every time we go up. That puts us at negative 2 degrees Celsius. And if we go one more level up to 5,000, because we gotta stop somewhere, our temperature of that air parcel is going to be negative 8 degrees Celsius. So there you have it. From the surface to whatever level your dew point temperature is at, whatever level it takes to get to that dew point temperature, you use the dry adiabatic rate. Once you have hit that lifting condensation level, you switch to the moist adiabatic rate. And if you're wondering if that's something we're pushing that air parcel down back towards the surface, you just do exactly what you did in reverse. You take that negative 8 degrees Celsius at 5,000 feet, you move down to 4,000, you're adding 6 degrees Celsius back because it's still saturated, which puts you at negative 2. You move down to 3,000, take away 6, add 6, and you are now at 4 degrees Celsius. Add another 6 degrees, and you get to 10 degrees Celsius, which is our dew point temperature. So we are going to now switch back to our dry adiabatic lapse rate of 10 degrees Celsius, because from this point downwards towards the surface, that air is going to be unsaturated. So 10 degrees Celsius, 20,000 feet, go down 1,000 meters, 20 degrees Celsius, another 1,000 meters to the surface, and we are back down to 30 degrees Celsius. There's a little catch to that we will get at some other point along the lecture. But right now, that's how you do it. And this is where we are going to end our section on atmospheric stability, lecture part 1.